Hi, this is Involved Innovation YouTube channel. In this series of video, we will see about the number theory required for competitive programming and all the programming coding interview. First, we will see about prime numbers. We will start with how to check if a number is prime, and then we will also see about the factors of a given number and prime factorization of a given number, because a number can have only one prime factorization, and in that way we can also discuss about one of the very important algorithm in prime number, which is Sieve of Eratosthenes, and we will also discuss about the time complexity of Sieve of Eratosthenes. A number which is divisible by only itself and 1, it is called as prime. That number need to be greater than 1, because the smallest prime number which we have is 2. 1 is not considered as a prime number. For example, let's take this 13. 13 is divisible by only 1 and itself 13, so this is prime. If you see 14, that can be divisible by 2 and 7, so that is not a prime. Then it is said to be composite number, and that is not a prime number. This is a brute force solution for determining whether the number is prime or not. If the given number is 1, then obviously that is not a prime number, so we are returning it as false, and we are running from 2 to n minus 1, and then here we are checking whether it is divisible by 2 to n minus 1. If it is divisible by 2 to n minus 1, that means this is not a prime number. This is gonna be a composite number, so we are returning false here. And then if it is not divisible by anything other than 1 and n, then obviously this is a prime number, and we are returning true here. So time complexity of this algorithm is order of n. Can we able to improve this algorithm? Yes, there is scope for improvement in this algorithm. So we will first think about how we can improve this algorithm. We will see about the factors. So here 72 has factors such as 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36 and 72. Factors are numbers which are divisors of this particular number 72 here. I have written a simple Java code to get the factors for the given number n. The time complexity of this algorithm is order of n. And here we are checking whether the number is divisible by I. The I ranges from 2 to n. If it is divisible by I, then we are adding that I to the list. That list has the factors for the given number n. And then if you try to combine these factors, we can able to form groups here. That is 1 into 72 gives us 72. 2 into 36 gives us 72, 3 into 24 gives us 72, 4 into 18 gives us 72, 6 into 12 gives us 72, and 8 into 9 gives us 72. So all the factors I can able to club together to form a pair. The product of each pair is the number n. Here the first part is less than the square root of n. The square root of 72 is approximately 8. So first part we will have always values lesser than the value 8, and the second part will have always value greater than 8. By this way we can check only from 2 to square root of n. We don't need to run from 2 to n, and we will prove this by contradiction whether this holds true for all the cases. Here we will take 3 cases. In the first case we will think about what if our factors are lesser than the square root value. Let's take a is lesser than the square root value, and then b is lesser than the square root value. Obviously this will always gives us the value lesser than n. Value 144, then the square root of 144 is 12, and then if you have a value lesser than 12 in a and b, then we won't be able to reaching up 144. So this doesn't hold true. In the case 2, we will take the a factor is greater than the square root value and the b factor is greater than square root value. Here also we will take the same example 144, and the square root of 144 is 12. So if you try to multiply two values which is greater than 12, obviously we will be reaching up value greater than n. So this is also not possible. So if these two cases are not possible, then by contradiction we can able to only achieve this with case 3. Let's take a is lesser than the square root value and b is greater than the square root value. Multiply that, then we can able to reach the value n. So this is the only case which is possible. We are safe to say here, like, one of the divisor in a pair must be lesser than the square root value. So it is enough to start from 2 and check only till the square root of n to find whether the given number is prime or not. We can improve the algorithm time complexity to order of square root of n. So we no need to really check till n. We can stop till the square root of n. So here I am starting with n equal to 1. If the n is 1, then obviously we are returning false. So here we are checking for each value from 2 to square root of n. If that divides the number without any remainder, obviously then that is not a prime number, that is going to be a composite number. So this is an algorithm which has the efficient time complexity square root of n. So with this understanding, we will see about very interesting problem. Each and every number will have only one unique prime factorization. We will see this with the example. We have 88. Here the 88 can have a pair of factors like 8 and 11. 8 has only one unique prime factorization, that is 2 to the power of 3. So here the prime factorization for 88 is 2 to the power of 3 and 11. That is the only prime factorization available for the given number 88. We will see this with a bigger example. 2088 factor 29 into 72. 29 is a prime number and 72 has a pair of factors like 8 and 9. And 8 has a prime factorization 2 to the power of 3. And 9 has unique prime factorization, that is 3 to the power of 2. For the number 2088, there will be only one unique prime factorization, that is 29 into 2 to the power of 3 into 3 to the power of 2. Discuss about one other interesting problem, that is finding prime factorization for a given number n. So first we will go with the name solution. Here we will start with a list. So that list holds a string. Here the string will be the prime factor and the power of that particular prime factor. So here in this algorithm, we are starting with I value 2 and then it goes on till n. We are checking whether the particular I is a factor of n. So if that number is factor of n, then we are dividing that n by the particular I and then we are incrementing the count and we are checking whether the n is still divisible by I. If it is still divisible by I, then we are incrementing the count. We are continuing this loop till the n is not divisible by I. This prime number has the power of count for the given value. And we are continuing this till the value of n. So this might not be really needed based on our understanding that only one prime factor will be greater than the square root of n. So with this understanding, we will run the loop starting from 2 to square root of n. If the resultant n is greater than 1, then we will add that value to the list. Because here we are dividing this n and here we will attain a point where there will be no prime divisors which divides this number and which is lesser than the square root value of n. If the given number doesn't have any prime factors less than square root of n, then it will have only one prime factor which is greater than square root of n. We will be just checking if n is greater than 1. So that means this number n has one of the prime factor which is greater than square root of n. So we can simply add this power as 1. So now we will see this with the example. Let's take the number 88. So first we are starting with the I value 2 and then here we are checking 88 is divisible by 2. So if 88 is divisible by 2 completely without any remainder, then we are going inside this while loop. 88 is completely divisible by 2. So here we are incrementing the count and we are storing n as 44 here and we are going it again. 44 is divisible by 2. Then we are going again and we are incrementing the counter. Now the count value is 2. 44 divided by 2 gives us the value 22. 22 is still divisible by 2. So we are increasing the counter. Now the count is 3 and then the value of n is 11. The 11 is not divisible by 2. So here we are trying to add the string 2 to the power of 3. And next value of I is 3 and 3 into 3 which is 9. 9 is less than or equal to n. Here n is 11. So we are continuing with this loop and 11 is not divisible by 3. So we are going ahead and we are incrementing the value of I. Now the I value is 4. 4 into 4 gives us the value 16. 16 is not lesser than the n value which is 11. So we are breaking this for loop and then we are going here. So here we are checking the n value is greater than 1. Here the n value is greater than 1. That is the n value is 11. So we are adding a string 11 to the power of 1. Next we will see about one of the very important and interesting algorithm which is Sieve of Eratosthenes. We need to find all the prime numbers from 1 to 100 and how we can able to find it efficiently. That is what we can able to achieve with Sieve of Eratosthenes. 1 is not prime number, so we are leaving out 1. So we are starting with 2 and we are incrementing 2 here. 2 plus 2 gives us 4, 4 plus 2 gives us 6, 6 plus 2 gives us 8, and we are running till n, and we are striking out all the numbers because those numbers are not prime. So here we have completed our loop with 2. So proceeding with the next prime number, which is 3. 3 is prime because this is not striked out. So we are incrementing 3 plus 3 gives us 6, 6 plus 3 gives us 9, and it goes on till n. So here we are striking out all the values which are increments of 3. Next we have the prime 5 because that is not divisible by any of the previous numbers 2 and 3, and the increments of 5 are 5 plus 5 gives us 10, 10 plus 5 gives us 15, 15 plus 5 gives us 20, and we are continuing this till the n. So we are striking out all the values which are increments of 5. Next we are continuing with the next number which is not striked out, so which is 7. So 7 is a prime number. We are striking out all the increments of 7. 7 plus 7 gives us 14, 14 plus gives us 21, 21 plus 7 gives us 28. So here we have striked out all the numbers from 1 to 100 which are increments of 7. In the previous understanding, we have seen it is sufficient to run only till the square root of n. Square root of 100 is 10. So here we have run from 1 to 10 because 8, 9 and 10 are not prime, so we no need to continue with those numbers. So we have arrived with our prime numbers which are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. These are all the prime numbers which are available from 1 to 100. So now we will write a simple program to implement this Sieve of Eratosthenes. So here we are starting out with a list of prime. The list of prime is to collect all the prime numbers from 2 to n. So here we have an array, and this array holds values starting from 0 to n plus 1. In this array we are initializing each and every value to 0. And then after completing this iteration, we are checking whether the value of a particular index in the array is equivalent to 0. If the value of array for the particular index I is equivalent to 0, then that means the I is a prime. We are checking from 2 to square root of n. So here we are checking the number is prime. So here we are running the inner loop only for the prime numbers. We are not running this for all the numbers. So we are starting with 2. As we have initialized all the values in the array to 0, initially the 2 will be holding 0 here. We are running this inner loop, and this marks all the increments of 2 with the value I. So here we will have the first value as 4. Array of index position 4 is equivalent to 2, and then here we are running this loop till n. And the next index value is 3, and 3, the array third index is equivalent to 0. So here we are continuing with our inner loop, and here we are marking all the increments of 5 array values to 3, and then we are continuing with the next value which is 4. So here the array of 4 is not equivalent to 0. It holds a value 2. So we are continuing with the next I value which is 5. Array index 5 is 0. So here we are marking all the increments of 5 index value in this array to 5. Next we are continuing with 6. 6 index position in the array is not equivalent to 0. Next we are continuing with 7. 7 index position in the array is equivalent to 0. So we are marking all the increments of 7 to 7. The next value for the I is 8. The index position of 8 in the array is not equivalent to 0. The next value of I is 9. The index value of 9 in the array is not equivalent to 0. The next value is 10, and the index value of 10 in the array is not equivalent to 0. So 11 into 11 gives us the value 121. 121 is not less than or equivalent to 100. So we are stopping the loop here. So here we have a loop just to get all the prime numbers. So here we are checking array for the given index I is equivalent to 0. If the array of index I is equivalent to 0, that means that number is prime. So we are adding I to it. So this is how we can able to find all the prime numbers from 2 to n. The time complexity of this algorithm is n log of log n. We will understand this time complexity. First we will start with the inner loop. For inner loop, it will execute, for the first iteration it will execute n by 2. That means if you have n as 100, the increments of 2 is 100 divided by 2, which is it will run 50 times, and for the next iteration it will run the increments of 3. So the n is 100 and we will have the increments of 3, which is 100 divided by 3. For the next iteration we will have 4 and it is n divided by 4. So we can write this equation as n divided by 2 plus n divided by 3 plus n divided by 4 plus goes on till n divided by n. N divided by n is 1. So this is harmonic sum. The time complexity of a harmonic sum is n log n. The inner loop is n log n. So here we are not running this loop for every value. We are just running this loop for prime numbers, and also we are just running this loop for values from 2 to square root of n. So the time complexity of this algorithm is n log n. Thanks for watching this video and share it with your friends if you like this content.